So thank you. Thanks very much for coming to the second day of the conference. So this morning, we're very happy to have Scott Armstrong again, moving now to, I think, quantitative homogenization. Yeah.
Thanks. So thanks for coming back to my second day of lectures. So I'm talking on the blackboard, yeah. So I'm going to talk about the first paper ever written on homogenization from a real rigorous math point of view, Giorgi. Okay, so in 1973, De Giorgi and Spagnolo wrote the first paper that I know about on homogenization. I never read it because it was in Italian, but then I realized that it was recently translated into English, so then I read it. And they had a lot of ideas that are the ones that we use still today. And so I wanted to talk about their perspective. So it's a little bit different than what I did yesterday. And I'm going to restrict to the symmetric case. So we're going to, just for simplicity, look at the case when our matrices are symmetric. Okay, so we can say A is equal to A transpose just at every point. And you can, redefine your probability space so that that's a condition of being in the omega, or you can say that that happens on an event of probability 1 or whatever. But so we're just going to assume that all our matrices are symmetric. And this allows you to, instead of thinking about the PDE like this, you can think about minimizers, local minimizers of an energy. All right, so this is Dirichlet's principle. You solve this equation if and only if you're a local minimizer of this energy when A is symmetric. When A is not symmetric, there's actually a variational principle that generalizes this, which is less well known, and you can use that to do this homogenization theory. But anyway, instead of thinking about homogenizing this equation, we're going to try to homogenize the energy functional. So we try to homogenize this variational principle, or this variational problem. Okay, and this is, of course, related to what the Italian school calls gamma convergence. So this is related to gamma convergence, which is another one of those words that I don't know much about because it sort of makes some abstract compactness definition that I can't remember, and I definitely don't understand. I do understand that there's a variational principle, and I can try to show limits of that. So that's what I'm going to do. But I know that I'm supposed to say that this is related to gamma convergence. So I think that is De Giorgi's fault that we have this term, but we won't hold it against him because he has a very nice idea here. Okay, so I hope the Italians don't get too mad at me for that. Italians are not too, there's not that much national pride, right? So they're not going to be that upset. Okay, so right, so what we're going to do is we're going to try to homogenize this. And so what does De Giorgi and Spagnolo do in this paper? They say, well, let's look at this quantity as a function of the domain. So we're going to take mu of capital U and the parameter E, and we're going to minimize this thing over capital U, the domain, that it has to be a bounded domain. I'll call it W like that. And so we'll minimize over W belonging to, and this little L is going to be my affine function. Okay, so let me explain this notation a little bit. So LE is going to now be my affine E dot X, okay, the affine function E dot X. So I'm asking that that W belong to H1 0, so the set of H1 functions with 0 boundary data plus the affine. So basically it has affine boundary data, okay? And I'm going to put a slash in the integral because otherwise I mess up all the volume factors, okay? So I'm going to do that. So now this is the equal to the energy divided by volume. So divided by capital U, the Lebesgue measure of capital U of the solution of the Dirichlet problem, if you want to think about it in terms of PDE. Okay, so you see that the minimizer is a linear function of the E, I guess. So it's because it's a linear function of the boundary data. And this is kind of a quadratic function of that minimizer. So this is going to be quadratic in E. So E maps to this quantity is quadratic. Now, what you would imagine, and also it's bounded because I put a slash here. So the A is bounded between little lambda and big lambda times the identity. And so you can see kind of from Jensen's inequality and things like that, that this quantity has to be bounded between lambda times e squared and big lambda times e squared. So in other words, it's quadratic, and I can write it as a matrix. I can actually write mu of u comma e equals, I can write it in terms of a quadratic form of a matrix that depends on u. Okay, so I write this matrix as A of u. And you may wonder why we choose this notation. Isn't A of x the field? Are you feeding the field A the set u? Why the notation? But I'll explain that in a bit later. But I do write it like that. So it's A of u. I'm not literally feeding the set u into the field A, but I'm just saying that A is the matrix for this. So this quantity has another property. It has a kind of monotonicity property, which is also important. So mu has domain monotonicity. Maybe I will go to the other blackboard. I'm starting to. So what do I mean by domain monotonicity? What I should really say is mu is sub-additive. Okay, and so what I mean by sub-additive is that if you take mu of if I have a domain and I cut it into pieces like this. Okay, so these are the ui and uj's, and this whole thing is u. Okay, this whole domain is u. And so I'm cutting it into pieces so that, okay, up to a set of measure 0, it's a partition. Then, and if I look at the mu quantity in this big domain for a given E, this is going to be less or equal than the sum of the smaller domains, summing over I in the partition. And I have to, so these are all of order 1, so this should somehow be a weighted average. So I'm going to weight by the size of the domain. And so that's the right way to write it. So this is sub-additive. This is what sub-additive means. Usually people don't write sub-additive like this. They usually don't have this weight in there, but that's because they don't have a slash in this integral. So if you take the slash out of the integral, write sub-additive the normal way, but then you see what happens if you put it back, you just get that. Okay, and I have to do this, otherwise I am off by r to the d everywhere, because I drop volume factors. Okay, and I like this way of thinking about it, that this is kind of a weighted average, or is bounded by a weighted average of these. So now, why is this inequality true? It's true because this is a minimization problem, and so if you minimize the energy in the big domain, the energy is less than any particular guess you might have for what the minimizer could be. And one guess that you can make is to take the minimizer of every subdomain, glue them together, and the gluing is okay because they have the same boundary data, and then use that glued function as a test into the minimization problem, and you get some inequality, right? And you get this. Okay, so that's kind of almost a trivial inequality that just comes from the minimized part of my minimization problem. Okay, so now this De Giorgi and Spagnola noticed gives some monotonicity, and you can use this monotonicity to make a limit of these quantities as the domain capital U becomes large. Okay, how is he going to De Giorgi and Spagnola? How are they going to prove homogenization using this quantity? The idea is that they're going to let this capital U become very, very large, kind of go to RD. So, and what you should expect to see, so what you would expect, so want to show the limit as capital U goes to RD. This is imprecise, let's just kind of go with it. This thing should sort of converge to, so this is a very big scale. This is the energy per unit volume in a very big scale. And we know from yesterday that the energy per unit volume is given by the homogenized matrix. It's also the flux per unit volume. But the energy per unit volume of the corrector is the homogenized matrix. Now, this is the Dirichlet problem with affine boundary data. So if you imagine the domain becomes very large, you're kind of restricting something to be affine on the boundary, but then sending the boundary to infinity, then you're going to make a kind of, hopefully, a kind of affine-like solution that exists in the whole space, maybe in the limit. And if you computed the energy of that per unit volume, that should be kind of like what we did yesterday for the corrector. And so this should, so you hope that this will give you some limiting, that you can take this limit and then you can call the limit a bar. Okay, so that's what you would want to show. And in fact, you don't need to show that it converges to a bar because we're not going to use the results from yesterday. We're going to pretend that we don't know them. So we're going to just show that this converges to something. So this exists. And whatever that limit is, you know that it'll be quadratic as a function of E. And so it should be given by some matrix because all of these matrices here are bounded between two multiples of the identity. So it should be a nice symmetric matrix. And so this should be given by some matrix. You can call that matrix A bar. So that's how you define A bar. Is this the matrix for the quadratic form, which is the limit of this as the domain becomes big. Okay, so the first paper in homogenization in terms of math, and that was really a rigorous math paper, proved homogenization in the periodic case like this. The proof basically works in the random case, but I think that they didn't know about the Ergodic theorem or something like that, or they didn't care to write it. And so later, a proof like this was done in the Ergodic case by Dalmasso and Modica. The authors are different, but it's still Pisa. So the thing I wanted to convince you of is that, so this perspective is nice, but I still want to convince you that if you can show that this quantity converges to this limit, that actually proves that homogenization happens. So that you may think it's nice having just this quantity converge to something, but how do I know that that completely allows me to prove a general homogenization theorem? Okay, I'll repeat your question.
You have this quadratic form mu u e.
Yes.
So the associated bilinear form does have a meaning.
So this is just some energy, and you want me to make a bilinear. Yeah, so you can make a bilinear form. And yesterday, when I found the correctors by solving the Lax-Milgram, or by using Lax-Milgram, that would be the bilinear form, sort of. But I mean, if the matrix is symmetric, a quadratic form characterizes the bilinear form. If it would not be symmetric, then there's a way to fix this so that it works in the non-symmetric case. Okay, and I'll tell you about that after. Okay, that's kind of a twist on the story. I don't know if that answered your question. So yeah, so this is not really limiting to the symmetric case, but it's convenient to talk about the symmetric case because if I write down the variational principle for the non-symmetric case, it's non-canonical in the sense that people don't know it. So it's less easy to understand. Okay, so anyway, this limit, if you show that it exists, not only is nice because it seems to be consistent with what we would expect from homogenization, it actually implies homogenization. So if you can prove this, okay, we get homogenization as a consequence. And I mean the full homogenization theorem that I sort of stated at the very end of the lecture yesterday. Okay, and the connection between this limit and homogenization is purely with analysis. Okay, it's completely like you can compute all the constants and everything. There's no mystery. So that if you had a rate of convergence for this limit, you would get a homogenization with a rate of convergence. Okay, so this connection is fairly robust in that sense. Okay, so let me try to explain a little bit why this is true. Why is it enough to understand just this energy quantity? Okay, so yeah, so this is my part B. So the reason that this is enough is because, so why does this imply homogenization? Okay, so there are various ways to see this. There's a million ways of proving this. But one way is to see that, which is connected to what we did yesterday, is to show that if this limit exists, then I can actually build solutions which essentially are the same as the correctors. They're not literally the same correctors that I built yesterday, but they have all the same properties and they're kind of the same up to a small error. So we can just use them the same way that we use the correctors. Okay, so how do we do that? Well, we're going to study, so let V of dot U and E be the minimizer. Be the minimizer of this mu in U, comma E. Okay, and let us. So, and I'm gonna remind you of my notation for. I'm gonna do kind of I'm going to take cubes and I'm going to cut them into smaller cubes. So I need to define these triadic cubes. Okay, so I have these triadic cubes. The side length is 3 to the n. If this is what the nth level looks like, then the n-1th level in 2D looks like this. Okay. So you can partition one set of, you can partition the cubes of n into the cubes of n-1. That. Okay, so this is my notation for that. And so what I'm going to do is I'm going to argue that if you look at the V in a very large cube, that it has to be kind of flat, it's going to have similar, after you subtract the affine, it'll have similar bounds to how we, to what we had for the correctors yesterday. And then I can use this thing minus its affine as a corrector, basically. It's essentially the same. Okay. And now what I'm going to do is I'm going to say, okay, if this thing exists, and by the way, this limit is supposed to exist, I guess, almost surely, right? So this is a P almost sure limit. So this limit, I guess, because I'm taking a limit, then I should call this thing an ergodic theorem. And so that's going to be some ergodic theorem gives me that limit. So it's going to be P almost sure. And if that limit exists, then it means that when I cut the cubes, when I cut a big cube into smaller cubes, and I look at the energy and I compare the energy in the big cube to the energy in the small cubes, kind of like through the sub-additivity relation, I know that that inequality is almost strict. Okay, that inequality is almost strict. Because the inequality is almost strict and my energy functional is uniformly convex, that means that when I did the gluing of the small scale cubes in order to test it in the big scale cubes, a variational problem, that I make a small error in the energy, and so I must have made a small error in the solutions, basically. Yeah.
Just to clarify one point, when you say the inequality is almost strict, you mean it's almost an equality?
Yeah, I mean it's almost not strict. Yeah. Thank you. Just helpful comments. Yeah. I mean the opposite of what I said. Yeah. I mean that it's not very strict. Yeah. Okay, so let me try to write this down. So we see this with a Poncare inequality. So what I'm going to do now is I'm going to define. So I need a little bit of notation. Vm is V in all of these cubes glued together. Okay, so I just mean that in every cube of size m, glued together over its lattice. Okay, so it exists in all of space. I just take the cubes, they partition RD. In every cube, I take the guy that that minimizes with the affine boundary condition. I glue them. It makes a perfectly nice function in H1 loc. It's locally H1. Okay, and I'm going to compare Vm to Vn. Okay, and so I'm going to let n be bigger than n. No. Yes, so m is the big scale, n is like a mesoscale, so you can think, so maybe m is like 100 and n is like 50, so they're apart by, so n could represent the square root of this big scale. And what I'm going to do is I'm going to use, let's see, do I have room? I think I'm going to start with a new blackboard, because I have an inequality to write. Oh, that's what that means. I have the same problem when I'm in Paris. I always push when I should pull and pull when I should push on all the doors. Okay. So here we go. We're going to compare now the scales. So I want to put lambda over 2 here. I'm going to slash in a big cube. So I'm just going to look in one copy of the big cube, and I'm going to look at the difference between the. Okay. And so first I'm going to write this in terms of the energy. Let me write this 1/2 inside. So now I should write grad Vm minus Vm dot A grad Vn minus Vm. Okay, because A is bounded below by little lambda as a quadratic form, so that's fine. Now this thing equals, so this is equal to the difference of the energies, okay, because the Vm is a minimizer. Okay, so this is actually equal to, now what is the difference of let me write it. Okay, so I'm just going to write, and I'm going to write the energies like the mu. The energy of this guy is this when I sum over all these cubes, which belong to the big cube, and I subtract the energy of the big guy. Okay, and actually, I'm sorry, I'm gonna have to put a slash in that sum. I actually put slashes in sums too. All the cubes are of the same size, so when I compute the energy of each little cube, it's basically making a slash in that sum. Okay. All right, so now this thing is supposed to be small, right? So if we believe the limit, then let's just call this thing the little o of one term. Because if m and n are both large, this should be small, if we believe that limit. Okay, so we're going to live with this thing being small. That basically means that these guys are close to each other, and that's what I said a second ago, right? When I was trying to say that if the energies are close, then the minimizers have to be close. I'm going to conclude from this that this guy is actually very flat, and it's flat because the glued guys have to be flat because they're pinned down to like a little mesoscopic grid, and by Poncare they can't move. They can only move inside of each little cell. Okay, so let's write that. I write that like this. In each little cell, if I look at Vn minus the affine, that means that this thing has zero boundary data, so I can apply the Poncare inequality. And I get constant 3 to the 2n, because the Poncare inequality constant is the size of the cube, but then I'm squaring it, so there's 2. The cube has side length 3 to the n, times the gradient in that cube. So I have this. Okay. But this thing is now bounded by the energy, because it's a minimizer in this cube. So this is bounded by up to capital lambda or something, grad Vn dot A grad Vn. That is mu. Mu is bounded, so this is bounded. Okay, so now I can triangle inequality, I guess, right? So now I should push here, right? So now I can do the same. So this is in every little cube. So I'm going to sum them all up and look at it in the big cube. And I'm going to look at the M one. Okay, so this is less than. Now you're allowed to use the triangle inequality with the square, right? But you have to remember to write 2. Tuomo laughs because he's the one that writes the 2s. I always just don't write the 2. Okay, so we have this plus now the Vn minus Le. Oh, there's a 2. You see the problem. Okay. So this one is now going to be controlled by Poncare because of this guy. But I'm going to pay the price of the Poncare constant on the big cube. But that's okay because it has a little o of 1. So this is now little o of 1 times 3 to the 2m plus c 3 to the 2n. Okay? And because n is going to be a kind of mesoscale, a little bit less than m, this is actually all going to be little o of 3 to the 2m. Okay? Because I'm going to, like, for example, you can choose n to be m over 2, in which case this is 3 to the m, which is way better than 3 to the 2m. Okay? All right, so now what have we proved? I said I was going to prove something like what we had yesterday.
Are you missing E in the first column? Not with Vn minus E, maybe?
Yeah, plus E, but E is, that's right. E is bounded though.
Yeah.
So I need to write another 2, right? So that, okay. Yeah, so, okay, so it should be 1 plus, because the norm of E is going to, so E is a unit vector. Yeah, thank you. So I should really split this into two pieces, yeah. Okay, thank you for that. Okay, well now, what do I have? I have that in the big cube, Vm minus Le, 3 to the minus 2, but actually let me just make it minus m and put a square root. That this should go to 0 as m goes to infinity, if we believe that limit. And we can, and so this is going to be our corrector. We're just going to call this thing phi m e. It depends on m. And what does this satisfy? Well, it satisfies the equation that this satisfies. This thing was a solution of the equation, but if I put the affine in there, I have to put it through the operator. So I have minus divergence a grad phi m e equals divergence AE, the same as the corrector equation. It's just in this bounded domain. Okay, so it's not, this is not stationary anymore. And you may think, oh no, it's not stationary, that's bad. Actually, that's good. Stationary is bad, contrary to what I was saying yesterday. And this thing equals 0 on the boundary. Okay, I'll give you more of the why stationary is bad propaganda later. But for now, just it suffices to notice that this thing is a solution, and I have correctors, and the correctors are satisfying the same bounds as I had before. Their oscillation, their L2 oscillation is like little o of the scale. Okay, and that's going to be enough to prove homogenization. Now I had more yesterday, right? I didn't just have this L2 estimate. I had H-1 estimates for the gradients and for the fluxes. So can I prove that? Yes, this Poncare inequality proof gives that. You just have to kind of think about, so this same proof, I won't do it again, but this proof also gives, when you kind of unpack what it's saying, you get this. H what hat. So I'm sorry I have all this weird notation. I need to put a 3 to the minus m. And then I need to add the fluxes. Okay, it says that this is going to 0. Limit, yeah. Okay, so this, it will give that if you think about this and rewrite it in terms of H-1. Okay, you still do a mesoscale and you use Poncare inequality like that. So now once I have this and it solves the equation, I can do all the same calculations I did yesterday and it doesn't change anything. So if you have a homogenization problem in a bounded domain and you're looking at this equation, you just have to you have to make sure that in order to use the correctors, if you're trying to understand this solution, a solution like this in some bounded domain, we're going to do the same way as we did yesterday and compare the U epsilon to the W epsilon. And you just have to make sure that when you do that, that the m is large enough given the domain and the epsilon. Okay, so you have to make sure that like 1 over epsilon u lives in your cube. And if that's the case, then you can use, okay, and it makes no difference then compared to what I did yesterday. Because they just have to be big enough that they cover the domain that you're interested in. Because if you go outside the domain, then the calculation breaks. Okay, so this was, all right, so that's the explanation of why this limit would give you the same stuff we had yesterday. And now I want to convince you that this limit should be true. Are there any questions about this, any of this?
What's the reason for doing, it's just a technical question, what's the reason for doing triadic as opposed to like dyadic or something for the decompositions? Just
you don't need to use the triadic. The triadic is nice because there's a middle one.
okay.
And if there's a dyadic, there's not a middle one. Yeah.
Sure. Okay.
I like, yeah. It just centers it. Any other questions? The hat. So I didn't explain the hat. So
right.
The hat. Okay. So when you ordinarily write H-1, you define it with as the dual of H10. But I need to allow my test functions to actually not be 0 on the boundary. So you can also you can also identify H-1 as the dual of H1 mean 0 functions, and it's a kind of stronger norm. So when you put the hat here, you're just saying I don't require the things I test against to vanish on the boundary, but I'm just going to subtract their means. Okay, so it's actually stronger norm. It's like, you know, there's a Poncare. I mean, you can define, if you have a Poncare inequality, you can make an H-1 space, but you have to, in any Poncare inequality, you have to rule out constants in some way. So you get a different H-1 in each way you do that. So maybe I'll move on and explain why this limit is true. So this limit is essentially the statement of what's called the Sub-Additive Ergodic Theorem. Usually ergodic theorems are stated in where the parameter space is one-dimensional. So you need a special multi-parameter sub-additive ergodic theorem. Okay, what it basically says is, okay, and you can prove it. What it basically says is, if you have a sub-additive quantity like that, so okay, so let me state it in all of its nice generality here. Please, I'm just going to hold this. Okay. What does it say? Assume P is just stationary. I'm going to run myself into the same trouble as yesterday. Okay, so assume it's just stationary, not necessarily ergodic. Okay, I'm really running a risk here. And let mu, which now the parameter E is kind of irrelevant for this, so let this be a sub-additive quantity. Sub-additive in my sense where I have these weights in there. All sub-additive quantity means is it takes values on all domains which are at least Lipschitz and bounded. Okay, and it gives you, it has to be bounded. So I need it to be bounded by lambda for some lambda. Okay, so the lambda is a deterministic constant. There exists a number, mu bar, which is going to be living in that space. That okay, so when I defined my spaces yesterday, they were vectors, and I used V. So this is not a vector anymore, but let's just go with it. This V invariant space, right? So this is the set of things which are, well, anyway, they're constant in space, and under the translation group, they're invariant, right? Something like this. So anyway, it's in this space. It's constant on all the ergodic components. If the probability measure would be ergodic, this would have to be a deterministic constant. Okay, such that the limit as t goes to infinity of mu of tu minus mu bar equals 0. P almost surely.
Finally, you also want to lower down on the view. I understand in our context it's not negative.
So I mean, unless there's a typo in our notes, I thought we proved it with only an upper bound. So maybe okay. I'll put this to be safe. I don't remember. It could be a typo in our notes.
Sorry, Scott.
Yeah.
Mu bar could be minus infinity. If all you have is an upper bound, mu bar could be minus infinity.
Yes. Yeah, that's right. So you need some way to keep it from being minus infinity. That's right. Okay, so let's just say that it's bounded. Okay, so this is the statement of the theorem. How does the proof work? Well, the proof works like this. First, you control the expected value, which is monotone. And once the expected values have converged, then the thing is kind of additive. And if it's additive, then by ergodicity, the fluctuations have to go to 0. Okay, so let me explain that in more words. Okay, so if you take expectations, because we have stationarity, which we like in this context, I'm going to drop the comma E, but you have this. Right, so this is decreasing because you go up to this line up there, and when I have my triadic cubes, this weight here is just putting a slash into the sum, and then you take the expectation of both sides, and everything that you're summing over is the same, and so you can just drop the sum. Okay, so you have this monotonicity. So the way that the proof works is you essentially wait, or until so choose a large scale until this is almost equality. Okay, so it's going to converge. It's a monotone quantity. If you wait long enough, it's going to converge. So wait until it's almost converged. And then that tells you that kind of in expectation, that thing up there is almost inequality. And that tells you that your big scale is essentially a sum of your small scale. Okay, so then after that, after this point, we know that a big cube equals the average of the subcubes plus a small error in expectation. And then this thing will experience contraction of its fluctuations. Okay, so this will experience fluctuation of its or contraction of its fluctuations. And that's because of an important property that this thing has that I didn't state in the theorem, which now I will. I also need that the mu of capital U depends only on the environment in U, or I should just say this is all a function of my A. So I'll just say it depends only on my A of X restricted to U. And because of that, each of these cubes is kind of localized to its area. And if you average a bunch of localized guys, then the usual ergodic theorem says that it will converge. So it'll converge almost surely, so its fluctuations will contract. Okay, so now this is how you almost prove the theorem. I said that the limit is almost sure, and I'm doing things where I'm making small errors in expectation. You may wonder, how am I ever going to make that an almost sure limit? And if I do this, I'm not. And so I have to do a bit better by using maximal inequalities. So I need to use maximal ergodic lemmas. And so maybe we can just stop it now because I'm not going to do that. Okay, but that's the basic idea. You wait until the sort of expectations converge, and then after that, you murder the fluctuations with the ergodic theorem. Okay. All right. Any questions about that?
So from this sketch of proof, you kind of see that if you know more about your guy, like independence or something like that, you get much better bounds, right?
So you want to know, yes. So if we would stop talking about just the ergodic case or whatever and try to make some quantitative assumption on the probability measure, could we, using this proof, get a rate for this limit? So that's a good question. So that was essentially, not quite, but essentially remarked in DeGiorgi's paper in 1973. DeGiorgi says that you should write these cubes and that you should compare one scale to the next and try to use a property like this, like independence or something, to get a quantitative rate. And he left it as a conjecture. Okay, so he stated a conjecture in his paper. And it was funny to find this written, like I found it like last summer because my new colleague is Guido De Filippis, and Guido was like, but what you say, it's kind of like what DeGiorgi was doing. And I was like, no, it's not true, Guido. And he like opened the paper and showed me the paper in Italian. And I said, Guido, I can't. But eventually I found this comment, and it's almost exactly what we ended up doing years later. So, which I thought was funny. So his conjecture that he states is not correct. You can't quite prove it like that, but it's in the right spirit of what you should do. So in the next hour, which I'm approaching the end, right? What time do I? Okay, so I'll say some more words, but I'll stop in 5 minutes. In the next hour, I'll explain exactly your question, like how do you make it quantitative? Yeah. So we would eventually like to understand one of these sets of correctors really, really well, because that would tell us then, because the machinery that goes from the correctors to the homogenization theorems is fairly robust and analytical, and there's no mystery in any of the estimates. But there's a kind of a mystery in these estimates. And so the key to proving, to making a quantitative homogenization theory is to find the right point in the right place to take this kind of limit and to quantify it in the, anyway, so with an independence assumption or something like that, you can do it. Yeah.
Sorry, I have a question about your remark about mu of U depends only on A of X restricted to capital U. Is that clear though in this setting with that, because your mu of U depends on your solution? But
I'm solving the problem only in U. So if you change the coefficients outside of U, it does nothing. Okay. So earlier I said that stationarity was bad, that we actually don't want stationarity, that these solutions that we're defining, they break stationarity, and that's really bad, and blah, blah. And the thing is you can't make things stationary and local, really. So you have to pick one, and you should choose wisely. So
yeah, so in your sketch of the proof of the ergodic theorem, the sub-additive ergodic theorem, is the sub-additivity is all going into these maximal ergodic lemmas? Because it seems like you didn't really use. Yeah, you have to prove the maximal ergodic lemmas, but there's a lot hiding. I mean, this would prove this thing in L1 or something. But if you really want the almost sure proof, it's stronger than L1. Okay, so where do you use the sub? Because it seems like you're just using the expectation. Like if you just said that these things were the same. I mean, sub-additivity is really
is really mainly used, or at least that's one of the main uses is there.
Okay.
And now to prove, I said that the ergodic theorem is really like a blow down Lebesgue differentiation. So how do you prove Lebesgue differentiation? You prove it for things that are smooth first by obviousness, and then you say like by the maximal inequality, I can go from the smooth thing to the L1 thing, right? You do the same in the proof of the ergodic theorem. Like there's a class of things for which the ergodic theorem is obvious, and then you switch to everything by a maximal ergodic lemma. And so this like switching is there, but you know, yeah, we were talking about this before the lecture, right? The proof is tricky, right? Yeah. So
Okay,
I don't want to do it. If I try to do it, I'll blunder it up. I'll write the inequalities backwards.
Okay. You usually it has a sign, so it's a small error in expectation is actually a small error.
You do need sub-additivity here. Like basically what you're doing is you're taking the linear maximal ergodic lemma that you needed for the first ergodic theorem, which is linear, and you need to show that it's still okay under this when you have one-sided linearity that is sub-additivity. Okay, and it's still okay. If you try to prove this theorem and you don't look at anything, this is where you'll get stuck, I think, because that's the tricky part, which is what I'm also not going to do. Okay, so maybe I'll stop and I'll do in the next hour, I'll finally talk about the independence and stuff.
Thanks a lot, Scott. Are there any questions?
There are already questions.
Yeah. Is it easy to see, for example, in the periodic case, the rate already from what you've done?
From this?
Yeah.
So that's what DeGiorgi and Spagnola did, is they did the periodic case using this. What?
In the quantified way. So
In the quantified way, yes, because yeah, so this should be easy because the periodic case is easy, so it's hard to decide when how much to cheat in the proof, right? Like, but yeah, these things are very. I mean, you can prove that they're close to the periodic solution, except for a boundary layer, and so.
Further questions? I mean, thanks, Scott, again.